sometimes we get transformation matrices that don't fall into the standard reflection or rotation, and we need to be able to explain what sort of transformation takes place when we perform the process of applying the matrix 2, 3, 0, and 1, for example. So we know that the image will be equal to the matrix, the transformational matrix, which is 2, 3, 0, 1, by the original point x, y. So if we were to, so any point in the Cartesian plane multiplied by the transformation matrix is going to give us this image. Now we can actually do some matrix multiplication here. So we've got 2x plus 3y. So turning 2, 3 sideways, 2 times x, 3 times y, 2x, 3y, you always add the two together. So you get 2x plus 3y, turn this sideways, 0, 1, 0 times that is 0 times x is 0, 1 times y is y, 0 plus y is just y. So we can say that the image x is equal to 2 times the x coordinate plus 3 times the y coordinate, and the image of point y is just equal to the y value. So with two-dimensional transformations, to explain what transformation takes place, we simply look at what happens to a unit square. Unit square is simply got side length of 1 and starts at the origin. So this will be 0, this will be 1, 0, 1, 1, and 0, 1. And this is 0, 0, obviously. So we're going to apply, see what happens to the point 0, 0. So you've got, when we do the transformation matrix 2, 3, 0, 1 on 0, 0, it's going to be equal to 2x plus 3y. We can do it using this here. So that'll be 0 and 0, so it has not changed. So the image of 0, 0 is going to be where it is. We then look at what happens to 0, 1, 0. So we've got 2, 3, 0, 1 times 1, 0. To get the result, it's just 2 times the x plus 3 times the y. So that'll be 2 and 0. And then we see what happens when the transformation matrix is applied to the point 1, 1. And 2 times x plus 3 times the y will give us 5. And just the y value does not change, so it'll go to 5, 1. And lastly, we've got to look at what happens. So you just look at what happens to the 4 vertices of the square. So 2, 3, 0, 1 is applied to 0, 1. So it'll be 2 times the x coordinate plus 3 times the y coordinate, so that'll be just equal to 3, and the y coordinate does not change, so that'll just go to the point 3, 1. So if we were to map what happens here, we've got 0, 0, 1, 0 goes to the point 2, 0, so it'll go to there. So if this is, say, P, this will be P dash, and it goes to 2, 0. So we call this P dash. And 1, 0, we call that Q. Q dash is 5, so we've got to come out here and up 1. So this is Q dash, which is 5, 1. And this will be R. So R dash is 3, 1. So we end up getting, it actually ends up being a parallelogram. This distance here would be 3, is 2, and that distance there is 2 as well. And the q distance has not changed. The y coordinates here have not changed for these points here. So this is one way of actually evaluating what happens with this transformation. You just look at what happens to a unit square and work out the coordinates of each of the vertices, and that gives you some idea of what is taking place with this transformation. That's for 2 dimension. If you have a 3 dimension, the matrix, the transformation matrix, would be a 3 by 3. And you would have to look at what happens to, because you've got 3 dimensions now, so this is for 3D, and you'd look at what happens to a unit cube. In this example we looked at what the transformation did to a unit square that had side length unit being 1. Here you've got a unit cube, so you'd go 0, 0, 0, 1, 0, 0, 0, 1, 0, etc., etc. So you would actually go around the vertices of the cube and see what happens to those points. So that's a way of interpreting some sort of geometrical interpretation of what happens to transformation matrices.